Hello, everyone. I'm Jared. I'm a PhD student at BU. This is my first Bridges. I will like to return after this, and I'm just glad that I get to contribute in some small way. So I'm going to talk about a three-dimensional lattice that I learned about a couple of years ago. It has a lot of different names. Because for about the past century, it's been talked about in many different contexts, in math, in physics, in art, in chemistry, in crystallography, independently discovered many different times. I think the most common name for it is the Laves graph. I learned it as the trihelical square tiling, or TST, so that's what I've been calling it for this project. Can I get a sense of who's actually acquainted with this already, who's heard of it? Okay, that's not so bad. I'll still be explaining it to everybody. Some of its properties include that it is chiral, it's triply periodic, and it is vertex and edge transitive. And there's actually a fairly small number of lattices that have all of these properties at the same time. And one more feature, as shown in the rightmost diagram, it's intimately related to the gyroid minimal surface. So here's a slightly better look at it. And the key thing that I want you to pick up on is as it rotates by, you see a lot of different patterns, but in a particular one is these squares start to show up right about now. And you see these like square helices appearing and pointing towards you. And what's really nifty is that there's actually three orthogonal sets of square helices that are spiraling in the X, Y, and Z directions. And I have them in, so blue just passed by us, green is approaching as it rotates around, and red is going vertically. And when I learned about this, and these three sets of helices constitute the entire lattice, but no one of them remove any one and you don't have the whole lattice anymore. And I just found this really visually fascinating. Even more interesting is that, I just talked about, here's the projection down of those square helices. And while there are three sets of square helices, there are simultaneously four sets of triangular helices that themselves also constitute the lattice. And they're a little smaller. And collectively, here's something showing all of them. You have the lattice in red, you have the square axes, the orthogonal square spiraling axes in green, and you have the four triangular axes in blue. And together, they actually correspond to the faces of a cuboctahedron. So I thought this was all really nifty. I was really drawn to all these different helices, and I wanted to hold it in my hand. So I was like, how can I make a model with the tools that I have at my disposal? Artistic interpretations of the TST under various names have existed for some time, and from folks at the conference with us today. I specifically wanted to create something that was modular, was 3D printable, because that's what I had, and specifically resembled the lattice rather than these other interpretations which focus on other properties of the shape. And I also wanted something that would show off these sets of helices that were so interesting to me. The key property that I worked off of was the fact that every vertex is trivalent and is coplanar with all of its neighbors. And what this means is that any two vertices have a sort of plane dihedral angle between each other, and you can derive it easily enough. Interestingly, if you build the TST with these sets of three coplanar vertices and you build it out, the only angle that will give you a valid lattice that closes up on itself is this angle. The other one, actually, there's a degenerate angle of 0 degrees, and then you just get the hexagonal tiling of the plane. One thing that I would love to explore in the future is in other geometric spaces, like hyperbolic space or whatever, are there other angles that produce other interesting lattices? So with this in mind, I got to work on some prototype designs that I could 3D print. I started by having each vertex be this, three-pronged thing, and then have the edges enforce that dihedral angle. And then I realized, well, you can actually combine the two pieces together into one sort of three-spoked design. But the key thing is that you need to design a joint that when you put two pieces together, they join symmetrically to each other and enforce the angle properly. So after a couple tests, I came up with this design, which had good tolerances so that I could fit the pieces together like a building toy. And it kind of looks like the sort of joint is vertical, but in fact it's offset by that dihedral angle, so that when you put two pieces together, you get the offset angle that you want. And what's nifty is that because of the intrinsic symmetries of this lattice, it's impossible to put two pieces together incorrectly. So you put pieces together, you flip it over, put it back together, you get the exact same results. So it's impossible to do this wrong. So I printed out a bunch of these, and what I got as a result was this little model, sculpture, whatever you like. I had the pleasure of exhibiting it at the Joint Mathematics Meeting Art Gallery earlier this year. And here are a couple different angles of it. I included visually in red the square helix axes, and in blue the triangular axes, so that when you're looking at the sculpture, you can actually point your view down one of the axes and you can see the square helices on the right pop out, or on the left you can see the triangular ones. Here are humans for scale. And I also included some extra pieces at the gallery that people could play around with and put together, and a bunch of them broke, but that's okay. I'll engineer them better next time. People seem to enjoy it well enough. What I noticed by spying on people who were looking at my piece for research purposes was that people weren't really looking down the axes. And as you walk around the piece, and I wasn't able to bring it to the conference here, unfortunately, but as you walk around the piece, you see all these different patterns pop out, but I don't think people really had the instinct to look down the axes. So where do we go from here? I have ideas, and I want to hear your ideas because I'm only scratching the surface with this. And here's idea number one. I'd like to design something that can show all 7 sets of helices in distinct colors, so that when you look at the sculpture from an appropriate angle, that color pops out and you can see the triangles or you can see the squares. Now, I know that this can be done with just the squares, as we saw before, with 3 colors. Now, the visual result, the effect of that in person remains to be seen, the effectiveness of that. 7 might be harder to do, and may be much harder to do with a modular system. Another option is to have these square helices in one color and the triangular helices in another. That might work more effectively. Here's an example of a piece that does have 7 distinct colors for each set of spirals on the gyroid surface, which is great. It's just not specifically so it's possible in some kind of a way, but in a model that more closely resembles the lattice rather than the surface of the gyroid, that may be more difficult to achieve. Finally, I want to experience the infinitude of the lattice. On the right, here's a pretty crude render that I did using ray marching, and I think it'd be interesting to jump into virtual reality and explore it and see all the patterns pop out. Also, there have been sort of quote-unquote infinite pattern or sculptures created in the past using one-way mirrors. But if all you remember earlier, I said that this is chiral and your alarm bell goes off when you hear mirror. So obviously, if I created some sort of mirror setup with a piece of this lattice that you could look at it infinitely, it would reflect, and the spirals would be going in opposite directions each time it reflected off into infinity. And maybe that would be a cool visual effect in and of itself, but I'd be curious to see if there's any way to create an infinite effect despite the fact that it's a chiral structure. So happy to hear any ideas. I'd also love to hear, like I said, because the work and research over the last century into this structure has been so scattered across disciplines and under many different names, I'm only seeing like a couple things over time pop up as I learn more about this. So if any of you are aware of things like this into the Laves graph, trihelical square tiling, whatever you want to call it, I'd love to hear about it because it's sort of all over the place, like I said. So that's all I have for today. I really appreciate you listening, and I hope to be back in the future with some more results and maybe some more artwork.
We have time for questions. Go.
Maybe not a question, but a remark. You know that this lattice also has a nice
property of being energy minimizing, and it only shares that property with the diamond metals?
Right. So that relates to its relationship with the gyroid, I guess, as well, right? That it's a minimal surface,
Maybe.
maybe. Yeah.
I wonder if your goal is to have people look down these areas rather than coloring it, which sounds hard. You could just mouse up little tubes and say,
Look through here. Yeah, that's true. Another idea that that somebody had was embed it inside of the cube octahedron, like I had shown, and the instinct will be to look straight at the faces of the cube octahedron, and then you will see the squares or triangles pop out. So that's something worth exploring as well.
I question myself. You mentioned the mirror, but perhaps it's stupid. But if you take two mirrors, for example, if you have two mirrors in a corner,
Right.
You look into that, you're not reflected.
You have it sort of double reflect every time, and the end result is that it doesn't reflect at all. Maybe. I haven't seen anything like that done, and I don't know what the experiential result of it would be, but it's all worth exploring. It's also interesting because I'd be putting it, all of these kinds of infinite sculptures that I've seen usually they're infinitely repeating the thing the outermost shape, like that cube, for example, rather than having something on the inside that's repeating infinitely. So that may have a different visual effect as well. Mm-hmm.
I'm somewhat surprised by the statement that you made that when you have a real physical object and give it to people, that they're not looking down the axes. Because when you're using the CAD tool and let the thing rotate, every time you look down one of the channels, it really stands out and you want to stop there.
Yes.
So what is different when people manipulate this manually, and what's psychologically going on here?
I would say one of the most important things is that real life is not orthographic. So if you're looking at this in CAD orthographically, it kind of looks like a big mess until suddenly, all these squares pop out, or all these triangles pop out. And there isn't a particularly good way of I think there are some techniques that you can sort of approximate, infinite focal length or zero focal, whichever one it is. But yeah, that's probably the key difference.
So maybe a much larger scale when people, were a long distance away or so, like.
Or make it really small. You hold it here, and then
yeah.
That's another thing I want to do is it. Or closing one eye will do. It'll help. Yeah.
I was gonna say, so you had that one where it was rotating out of the 3 different colors.
Mm-hmm.
Well, have you thought about 3D printing it in 3 different colors? Or do you have access to a?
I might have access. I haven't tried that. I came up with that visual in the process of working on this presentation. But yes, the colors that can do, printers that can do multiple colors, that's the most straightforward solution to that, sure.
Because I've made a few sculptures where it's kind of like an alignment thing, and it would be so satisfying to play with that with the 3 colors in person.
Yeah. And each piece, I think, is identical, where you have this little green bit and this little blue bit and this little red bit that sort of twist past each other. So I think it would be possible to build modularly.
Okay, thank you very much.
Well,